Okay, so let's start. So our mathematician spotlight today is Kathryn Lindsey, who is an assistant professor at Boston College. So the other day, do you remember we had all these beautiful Julia sets on the screen, and they were so beautiful? Okay, so here's some of the Julia sets. So this one is known as the airplane. Can you see why? Looks kind of like an airplane, yeah? Pretty good. And then this one is known as the rabbit. Can you see why? It's a little harder to see, right? It's a deformed rabbit. Yeah, it's a little harder to see why this would be the rabbit. Okay, so, but it takes the name of the rabbit. So this is Kathryn Lindsey. Kathryn and her PhD advisor, Bill Thurston, looked at this and said, you know, it doesn't really look like a rabbit. I wonder if we could make a Julia set that legitimately looks like a rabbit or like any other shape that you might want. So these Julia sets are of quadratic functions. So functions of the form f of z is like some amount of z squared plus some amount of z plus some amount of constant. And so when you're making different Julia sets, you only have, actually, that's not quite true, I don't think. Actually, but in any case, no, maybe it's true. Okay, something like that. You only have these three parameters. If you want to have different shapes of Julia set, like this airplane or this rabbit, you've only got these three parameters, A, B, and C. And they said, what if you let yourself go higher? So maybe you could get a Julia set that approximated anything that you wanted. So they showed that if you allow your polynomial to get a higher degree, you can approximate any shape that you want. So the shape that Kathryn wanted to do, here's Kathryn again, was her cat, Magellan. So here's a Julia set that really looks like a cat, right? It's not like, I kind of see the cat. No, you see the cat. And for this, they used a polynomial of degree 301. And they showed that you can do any shape, where I'm using the word shape to mean like one shape, like not a smiley face with two eyes and no, just one piece. If you just draw any Jordan curve, which is a closed shape, you can get a Julia set that approximates it arbitrarily closely depending on how high you're allowed to go in your polynomial. So here they did a pretty good job with 301. If they had wanted to go even better, they could have had like a 3,000 degree polynomial or something like that. Pretty neat, huh? All right. So, and this is ongoing, and she's extended this to shapes with like one hole inside. So it could be like a winking cat, a one-eyed cat. Yeah. Okay. So, good. Oh. There. Oh, actually, this one. Okay. So here's what we're going to do. Last time we talked about optimizing functions, like maximizing and minimizing functions. We talked about how this is useful because there are things in your life you might want to maximize, like happiness. And that's a function of several variables, and you'd want to maximize it, of course. Or you might want to minimize something else, like you might want to minimize the amount of stress in your life or something like that. And it's great if you can just have any inputs to your variables that you want. But often in life, the things that we wish to maximize and minimize have constraints. Like I wish to minimize the amount of stress in my life under the constraint that I still have to take 4 classes and learn lots of stuff from them and pass my classes. So they're optimizing under constraints. So the kind of constraints that we think about mathematically are like, I want to maximize this function over this region. So my favorite kind of function maximization is high points. So I like going to the high points of states. So I have handed you a map of the 50 United States. And on the map, it shows each of the high points, which are red, and then the low points. And so here's what I'd like you to do. Pick 10 states. You don't have to, if you don't know what the states are, you can just like label them A, B, C, and such, if you don't know which ones they are. And say whether the high point occurs in the interior of the state, or on the edge, or at the corner, or somewhere else. And then when you're done with that, if you could, so Colorado, the high point occurs at an interior point. And so basically around there, the topo lines look something like this schematically. And so can you make a plausible idea for how they extend so that the high point of Kansas occurs on the boundary and so that the high point of Nebraska occurs at the corner. Like keep these guys going to figure out how that would fill in to make these the high points of these states. Okay? Ready? Go! Okay. Hey, so can you name some states where the high point occurs on the interior of the state? Colorado, yes. Washington, indeed. California, yeah. Wyoming, I agree. Arizona, yes. Okay, good, good. And many more, yes, many more. New York, Pennsylvania. Okay, how about along the edge? Illinois, yes. Montana. Really? I would guess that was a mountain, but I'm not sure. It's without further. I'm not sure. I'm not sure about that. It might be. It might be. What else? What else did you say? Nevada. Somebody said. What did you say, Yash? Florida. Florida. Maybe. Yeah. Florida's a tough one. Does anybody know what the maximum elevation of Florida is? Can you guess? It's like around 100 feet. It's a very low state. So there's actually 6 different points in Florida that are all equally the highest point to within the range of error of the measuring device. So it's kind of hard to say, but there's one that's accepted. Maybe it's along the edge. Yeah, any others? Along the edge? Yeah?
California.
California is on the interior, I think. I think there's actually a...
Oh, sorry, I meant Nevada.
Nevada. Nice. Okay. Great. Yep, I agree. Okay. Kansas and Kansas. I agree. Yes. Okay, how about the corner? Anything on the corner? Mississippi. Mississippi, I think, is in the interior. I went there. Wyoming. Wyoming? Wyoming.
Right here.
I'm not sure about these. Any for sure? Nebraska for sure. Yes, Nebraska for sure. Oklahoma for sure. Yes. Connecticut, I think that one's for sure. Mississippi, we weren't sure about. I think I went there and it wasn't on the actual corner. It's near the corner for sure. Massachusetts also near the corner, but not on the corner. It's hard to tell from the map, yeah? What?
Connecticut and Massachusetts, the southern one. Oh, yeah.
Connecticut, I think you're right about Connecticut. New Jersey maybe, Pennsylvania maybe. Okay, so some of these, it's from the level of resolution of our map, it's not clear whether they're exactly on the corner or whether they're on a mountain that's near the corner. So for sure, Mount Greylock, for example, a mountain that's near the corner of the state. Okay, how about elsewhere? Did anyone find a high point of a state that occurs somewhere other than the interior, the edge of the corner? Yeah, right. Okay, this can happen. Okay, good. Okay, I agree. Yeah, so the point of this exercise is to have fun and look at high points and love our states, and also to know that the maximum and minimum of a function like elevation on a constrained region like a state can occurs either on the interior, the edge, or the corner. That's it. So if you have some sort of function and you want to find its maximum and minimum, you have to check the interior, the edges, and the corners. And that's it. How about this problem? We had to make level curves that plausibly explained the arrangement of things. Was there one more thing? Yes. Oklahoma. Okay. So the idea is that the high point of Colorado is here, but maybe the high point of Kansas here, maybe it isn't the case that there's a mountain right here on the edge. That seems unlikely. And maybe there isn't a mountain right here at the corner of Nebraska. So maybe it's just that the whole west is sort of sloped down this way. And so Nebraska gets its highest point just by sticking out into these high elevation places. Yeah, this one is in a cornfield, essentially. Actually, it's a bison raising area. And you would not, it's not mountainous. It's just a field, but yet its elevation is like 6,000 feet, which is pretty high. So, Okay, so the idea is that these level curves, maybe around this high point of Colorado, just make it so that this point of Nebraska is just the highest point of the state. Everything else is lower. This is a high, and these are getting lower. And then the same thing, this is not working out exactly. I'm going to have to amend my level curves just a little bit so that this point occurs here on the edge. So this way, in this way, the highest point of Nebraska occurs at this corner, and then the highest point of Kansas occurs in the middle, sort of in the middle of this edge. And the high point of Oklahoma occurs on the corner, also at sort of a random corner. There's a plateau out there. Okay. Good. Good. Okay. Okay. So this is for lovely states and elevations, but we don't have functions for the edges of states, and we don't have functions for the elevation. So we're going to do what we do as mathematicians and simplify it to something that we can analyze mathematically. So that's the plan. Yeah, questions or ideas about the highest points at any of that?
You've been to all of them.
What?
Have you been to all of them?
Have I been to all of them? I've been to 20 of the high points. So I had been to 10 by going on trips, and then last year I went on a road trip for a month, and I did 10 more. So actually I did some of them coming down the middle here, North Dakota, South Dakota, Nebraska, Oklahoma, and then I came through the south. So I did like Arkansas, Mississippi, Georgia, and then some of them in the Appalachia. Yeah, pretty cool, right? I recommend it. If you're ever going on a road trip or something and you need something to do, it gets you out into like the middle of nowhere type of places that you wouldn't go otherwise. Kind of fun. Okay. So let's find all the absolute extrema. So the maximum and minimum, the total maximum and minimum that occur of the function f of xy is x squared plus xy plus y squared minus 6y on the region where x is between -3 and 3 and y is between 0 and 5. So this region looks something like Colorado. It is a rectangle, something like this, where x goes from -3 to 3 and y goes from 0 to 5. So we have this sitting here, and then we have our function value, which you can think of as something like elevation. So it's sort of like a surface sitting above this region, and then we cut it off just at the part that we're interested in. So let me show you what this looks like. Okay, maybe a little darker would be good. Okay, so this function is sort of this bowl, this maybe, I think it's a parabola shape, and then we cut it off just on our region that we care about. So our here's, you can see it, yeah, you can see it. It looks like a hammock, sort of. So here's our plan. Our first plan is just going to be to find if there are any critical points of the function. So places where the x derivative is 0 and the y derivative is 0. So for us, that's going to pick out this minimum point here of the whole thing. Then we're going to check the edges, because we know our critical points, or maximum can occur either in the interior, the edges, or the corners. So we're going to check the edges. What we'll do is make the function, the one variable function, that is the function along just one edge. So this, you can see this curve, it's like a parabola on the far side, or this parabola here on the left side will have the function just constrained to that place. And then we'll find maximum and minimum of that, so that would pick up something like this minimum of this edge, this boundary curve. And then finally, we'll plug in the 4 corner points. So maybe for this, well, let's see. I think I already said the minimum is going to occur on the inside, like at the bottom of the hammock. Where do you think the maximum is going to occur? At a corner. I think so too. So that's what we'll expect. The maximum is going to occur at a corner. So now we know what to expect. Now we can do some algebra. Okay. 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 Ah, yes. The screen. Goodbye, screen. Okay. So, and then we'll keep a running list of candidate points. So, first thing to do is to find points on the interior. So places where the gradient of f equals 0. So let's find the gradient of f. Let's see, partial derivative with respect to x is 2x plus y, and partial with respect to y is like x y minus 6. Okay, so that we set that equal to 0, 0. The first thing tells us that 2x plus y is 0. We could solve for y. Y is negative 2x. Okay? And then the second one tells us that x plus 2y minus 6 is 0. But y is negative 2x, so we can plug in. So we get x plus 2 times negative 2x equals 6. So x minus 4x is negative 3x is 6. So x is negative 2. And then let's see, we know that y is negative 2x. So y is 4. OK, so we just have one critical point of the function, which we expected because when we graphed it, it looked like a paraboloid going up. So we are not surprised it only has this one critical point. So let's add that to our list, this point here. So there's our interior critical point is negative 2, 4. And on our picture, negative 2, 4, it's indeed inside, so we care about it. It's possible that it could have been somewhere outside, and then we would have said, throw it away, we don't care about it. Okay. Okay, let's do the edges. Okay, so the next thing to do is to do the edges. There are 4 edges. It's going to be a bit of work. We'll just do it. So there's like the bottom edge, the top edge, the left edge, and the right edge. So we have 4 edges to do. Let's do the first edge. So the first edge is the bottom edge, which is y equals 0. So the y equals 0 is a curve that defines that edge. So we plug in f of x comma 0, because y is 0. F of x comma 0, well, all these other terms cancel out, actually, so it's just x squared. So along the x-axis, the function just looks like x squared. We want to find the minimum, or any critical points. So f prime of x comma 0, derivative with respect to x is 2x. If we set that equal to 0, we get x equals 0. And what is y? You just point, oh, it's 0, yeah, because that's what we assumed. OK, so x equals 0 and y equals 0. So this is our first candidate point. So 0, 0. And indeed, it's in our region, so we care about it. Good. OK, second edge. Let's do the top edge, which is y equals 5. So this is f of x comma 5. So that's x squared plus 5y plus 25 minus 30. OK, so we want to see what the function is along that top edge. So let's take its derivative, set it equal to 0. F prime of x comma 5 is plus 5x. You're so right, 5x. X squared plus 5x. OK, so great. Now we can take the derivative. So 2x plus 5. That's the derivative. We want it to be 0. So this tells us that x is negative 2.5. OK, negative 2.5. And again, y is 5. So here's our second point, negative 2.5 comma 5. And before we put it on our list, actually, we should check if it's inside. So negative 2.5 comma 5. It is. It's in the part we care about right on the boundary there. Okay, let's do another edge. So our third edge, let's do the right edge. So that's the edge x equals 5. So f as a function of 5, x equals 3. So f as a function of 3 and y is like 9 plus 3y plus y squared minus 6y. So we can simplify. This is 9 minus 3y plus y squared. So the derivative with respect to y of this thing is just, what, negative 3 plus 2y. And set it equal to 0, we get y is 1.5. OK. So, and then x is 3. So there's our point. 1.5 comma 3. We should check if it's in our region. 1.5 comma, wait, sorry, 3, 1.5. That didn't make any sense. I was like 1.5 comma 3, but it's in the interior. Something has gone horribly wrong. OK, so I had to recheck. Good point. So it's x is 3 and y is 1.5. Good. Here we are. So 3 comma 1.5. All right, and then there's just one more edge. So the last edge, x is negative 3. So f of negative 3 comma y is, let's see, 9 minus 3y plus y squared minus 9y. So we can minus 6y. That was dramatic foreshadowing for when we simplify to get 9 minus 6y, nope, minus 9y plus y squared. OK, so the derivative then with respect to y is negative 9 plus 2y, which is 0. So y is 4.5. And x is negative 3. I'll write it up here so I don't get confused this time. There. OK, so negative 3 comma 4.5. Negative 3 comma 4.5. It's here. Good? So negative 3 comma 4.5. OK? So there's that. And then the last thing to do, part 3, is the corners. But here there's nothing to calculate. We just write them down on our list. So the corners are 3 comma, how about 3 comma 0, 3 comma 5, negative 3 comma 0, and negative 3 comma 5. So now we have all these points. Here they are. Let me add the corners. And these are all our candidate maximum minima. Yeah, Daniel? Yeah, is there any reason why the corners wouldn't show up when you're doing the thing on the edges? Yeah, so there is. So our picture here looks something like so, and then it kind of has something like that. Do you see kind of what's going on here? This is the surface sitting above a rectangle in the plane, or yeah. OK, uh-oh. It was going so well. OK, that edge is sitting along this corner. OK, when we do the edges and we take the partial derivative or the derivative along those edges, we pick up minima of the edge curve. So we'd pick up like this point here, and we'd pick up like this point here, and like this point here. And maybe this one doesn't have, maybe it just sort of keeps sloping down. It doesn't have, maybe this one doesn't have a minimum on that edge. So you only pick up like local minima. We're not going to pick up this point. Make sense? Yeah. Because the derivatives aren't 0 here. This is like the corner of Oklahoma. There's no mountain there, or valley or anything like that. It just happens to be going up. Yeah, good question. Yeah. So now the last thing to do is just you take all these things and you plug them into your function. So it's just a bit of work and trying not to make a mistake. And since that's not my strong point, not making mistakes on the board, I'm just going to write down what they are. So when you plug in negative 2 comma 4, you get negative 12. When you plug in 0, 0, you get 0. Negative 2.5 comma 5, you get negative 11.25. This guy, 6.75. This guy, negative 11.25. This first corner, 9. Second corner, 19. Next corner, 9. Last corner, negative 11. OK, so this, you just do a bunch of work. You plug it in. Now you get to pick which is the smallest and which is the biggest. Which is the smallest? Negative 12, yeah. Oh, there's a lot that are close, right? Negative 11, negative 11 and a quarter, and 12. But this one is the minimum. So congratulations, negative 2, 4, you are the minimum. And that's what we expected, because in our hammock, it looked like the minimum point was on the interior. OK? And then how about the maximum? 19, yeah. And that's what we expected, because it looked like the highest point was on a corner. So we're not surprised. But now we know. So we can triumphantly conclude that for this function, f of x, y, as written, on x between negative 3 and 3, and y between 0 and 5, the maximum is 19, occurring at 3, 5. And the minimum is negative 12, occurring at negative 2, 4. So now we know. And so if this were the state of Colorado, we would now know where the high point is and what the highest point elevation is. Yeah?
Curious how you did it on Grapher. You chopped off these boundaries.
Yeah.
How did you do that on Grapher?
So Grapher allows you to have a viewing window. So you can set the view. And so I set x to be between negative 3 and 3, and y to be between 0 and 5.
Oh, because that's an option that Grapher offers.
It's an option that Grapher offers. Yep. Yeah, other question? OK. OK, so I'll do one more example, because there are a couple things that are different about it. OK. So let's again find absolute extrema. So the maximum and minimum of the function f of xy is x squared times y on the region 3x squared plus 4y squared is less than or equal to 12. Well, that's different. OK, so the first thing to do is to figure out what this thing looks like. It's an ellipse. Yeah, it's basically like x squared plus y squared equals r squared type thing. But there's some different coefficients here. So first of all, let's figure out if y were 0. So now y is 0. We're on the x-axis. What would x have to be to get this to be equal to 12? Can you see? Plus or minus 2. Yeah, because then we get 3 times 4 is 12. So x is plus or minus 2 on the boundary where this is equal to 12. How about if x is 0? What should y be to be equal to 12? Yeah, plus or minus root 3. And root 3 is a little bit less than 2. So I'll draw those here. So the boundary of this, where this is equal to 12, is this ellipse. And then we want points where this number is smaller. So you see x and y have to be smaller. So it's close to the origin. So it's this region here. So it's like the filled-in ellipse. OK. So again, we'll just do our things. So find critical points on the interior. So we'll set the gradient equal to 0. The gradient of f is partial with respect to x, 2xy, partial with respect to y, x squared. Set it equal to 0. OK, I'll do the easiest equation first, which is the second one. X squared is 0, so x is 0. OK, so this tells us x is 0. Now, we already know that for any critical point, x has to be 0. So if you plug that back into this first one, it's already 0. So y can be anything. So actually, so y can be anything, and we get a critical point. So it's actually the entire y-axis that's the part of it that's in our region. That entire part is critical point. So that's this entire axis. Okay, let's actually make our list of candidates right now. So our first point is 0, comma y. Y can be anything in our region. And so this is a point, and this is the function value. Let's plug it into the function. What do you get? So you plug 0, comma y into our function. We get 0, yeah. So maybe we were a little bit worried that we might get different values for the function depending on what y is, but it's OK. We didn't. So now we know that whatever this surface looks like, it's sort of tamped down at 0. Maybe afterward it comes up like this. Who knows what it does? And I didn't graph this for you because Grapher doesn't allow you to cut things out in a circle. So I didn't do it. OK. Now, second part, the edges. So critical points of the boundary curve. Or curves. So in our previous example, our shape was a rectangle, so it had 4 boundary curves. It's kind of a pain to go through all 4 of them, although not so hard, because they were constants. We'll do that, but I just want to show you a clever trick of this one that we can do first. So here's a clever trick. You want to find maximum and minima of this function, x squared y, on the boundary of this, which is where 3x squared plus 4y squared is equal to 12. So a clever trick would be, how about I just figure out what x squared is in terms of y, and then I plug that in. So solve for x squared, solve boundary function for x squared, and then plug into f of x, y. So along the boundary, we have 3x squared plus 4y squared equals 12. Less than or equal gets you the inside, but the boundary is where it equals 12. So 3x squared equals 12 minus 4y squared. So x squared is 4 minus 4/3 y squared. So on the boundary, this is what x is in terms of y. X squared is in terms of y. Is it?
No, I was just thinking out loud.
Oh, OK. OK, so x squared is this. We have this expression for it. And now we know f of x comma y is x squared times y. But now we have x squared in terms of y. So we can write it as just a function of y. It's x squared, which is 4 minus 4/3 y squared times y. So let's simplify. It's 4y minus 4/3 y cubed. That's f of y. And now we can take the derivative. F prime of y is just 4 minus 4y squared. And if you set that equal to 0, you can see what? 4 equals 4y squared. 1 equals y squared. Plus or minus 1 equals y. OK. So now we can go to our picture. Y is plus or minus 1. That's like here. So here's y is plus 1, here's y is minus 1, and that intersects our boundary in 4 places. So that gives us these 4 points. And if you plug in, if y is 1, then this part is 4. If you subtract it, you get 8. So we would get 3x squared equals 8. So x is square root of 8 over 3. So I think we would get square root of 8 over 3 comma 1, negative square root of 8 over 3 comma 1, square root of 8 over 3 comma negative 1, and negative square root of 8 over 3 comma negative 1. So 4 points on the boundary. Yeah? OK. But that is a clever trick that worked nicely because our boundary curve and our function had something in common, this x squared, that allowed us to do this. So if you didn't have that lovely scenario, you could parameterize the boundary curve. So in our rectangle situation, which I just erased, there were 4 different boundary curves. But now there's only 1. So our method 2, so if we're not going to do the clever trick, we could do like a standard method. to parameterize the boundary curve. So our boundary curve is an ellipse, which is very much like a circle. If I wanted to make a circle, parametric equations for a circle, do you remember what you can do? Yeah, r cosine theta. So x is like cosine t, or theta, and y is like sine t, or theta. And if you do this, you get a unit circle. So in our picture here, if we did cos t sine t, we would get a unit circle. But that's not exactly our boundary curve. We want it to be bigger. So can you figure out what we would do to parameterize our ellipse? 2, yeah, we want x to be stretched by a factor of 2. You want it to be twice as big. You want it to go from -2 to 2, not just -1 to 1. So 2, and then for y, it needs to go from -root 3 to positive root 3. So root 3 sine t. Okay, so our f of xy, is x squared times y. So f of t, we'll put in whatever x is as a function of t, 2 cos t, square that, and then multiply by whatever y is as a function of t. So square root of 3 times sine t. Okay? So if we could multiply this out, I guess, we get 4 root 3 cos squared t times sine t. And that's f as a function of t. So this tells you whatever t is, what your elevation is on the boundary. So as you go around your ellipse as a function of time, it tells you how high your function is. Really great. And you want to know where this function has a maximum or a minimum. So you want to know where the derivative with respect to t is 0. So we'd take f prime of t, set it equal to 0, and solve. I believe that you could do this. So it would be 4 root 3 times some kind of product rule thing with cos squared t and sine t. So let's see. Derivative of the first times the second. Derivative of the first would be like 2 cos t times derivative of cos t, which is negative sine t, times the second is sine t, plus the first cos squared t times the derivative of the second, which is cos t. And then you'd want to set that equal to 0. So you can solve. So you can do this and you can solve. And it would be a bit of a mess, but we would get the same thing that we got from our clever trick. Okay, so this would give us, this gives us 4 points, as before. Okay? Okay, that's the two. So we did the interior, and we did the corner, and we did the edges, and now for the corners. But no corners. Yes. So there's no corners, so this is all we have to check. And now we have to just plug this into our function. So we already plugged 0 comma y into our function, and we got 0. Now if we plug square root of 8/3 in for x and 1 for y, can you see what we get? We get 8/3, yeah, because we square the 8/3 and we multiply by 1. So for these two, we get 8/3. And then for the ones where y is negative, we get negative 8/3. Okay, so that's what you just do the work, plug into the function, get the numbers, and now you get to do the fun part of looking which one is the biggest and which one is the smallest. So 8/3 is the biggest, so we have 2 equal maxima, and we have 2 equal minima. Yeah, okay. So the point of today was to look at an example of the states and see that you can get maxes on the interior, the edge, or the corner, and then see how to do it mathematically. All right, thanks everyone.